We'll start the last session of the day. Start with Markus. We'll go on exploring the land of Duality.
Yeah, thank you very much. And first of all, I would like to thank the organizers for giving me a chance to present some work here, and also for putting together this beautiful workshop. So yeah, I will continue with Chronicles of IIBordia Part 2, The Rise of Metaplectia. And this is mainly based on these two papers. So this is our long paper that includes also the map that you saw in Miguel's talk, and some work that we published roughly 1.5 years ago about duality anomalies. But of course, some of the things are closely related to this work with Jonathan, Miguel, and Ethan, especially that discuss the intricacies of this reflection 7 break. Okay, so in case you forgot about the Cobordism Conjecture or Cobordism Conjecture during the break, let me give you this one slide here. So all things must end, right? And that includes space-time. So this means that every quantum gravity theory should allow for a boundary condition. So why is that the case? Well, you can think about if there is an obstruction for allowing this boundary condition. So if there is an obstruction that tells you you cannot deform your space-time manifold to nothing, then this is a preserved global charge, as you learned already from Miguel, right? So from this, you can basically conclude that there are no conserved global charges whenever you imply that every quantum gravity has this boundary condition. That's the reformulation of the Cobordism Conjecture. Okay, so one simple example that is a bit different to Miguel's, but will be closer to what we're discussing in this talk, is take a two-sphere with a magnetic flux on it. Right, so this you cannot deform away because the magnetic flux would be a topological obstruction. It's a charge that you cannot get rid of unless you do something drastic to it. And this doing something drastic is including some defects that you heard about. So the reflection 7 brane would be one example, and we will generalize this to other defects. And basically it tells you that you allow some sort of singularities that then give you the chance to deform your manifold away. And for this simple example, which you couldn't deform away, you can just include the singular configuration of a monopole. And once you do that, you can get rid of magnetic charge, right? And then basically you can form a boundary where in the middle of this ball now sits a monopole. And you see that now you have this two-sphere with magnetic flux described as a boundary as you would like. And we heard that the mathematical framework of these deformation classes that contain some structure, which might be spin structure, orientation, some gauge bundles, whatever of this sort, is captured by these Cobordism groups, right? And you saw this picture on Miguel's slides and on Jake's slides, so I will not go into detail. So let us test the example now on the level of this Cobordism theory. So I told you we have a two-sphere with a magnetic flux on it. So the correct Cobordism group contains now, let's say we want also fermions, so we should have a spin structure. The two-sphere is two-dimensional, so that is this index 2. And we want a U1 gauge field. So additionally, we have maps from our space-time manifold into the classifying space of U1. Okay? So the Cobordism group we're interested here would be omega-2 spin with maps into BU1, and that contains a Z factor, so an integer factor, which is generated by two-sphere with magnetic flux given by the integer. Right? And this is exactly the Cobordism class that would be non-trivial, would pose an obstruction for a boundary condition, and is killed by including this now singular configuration. So the monopole in a U1 gauge theory is of course singular, so there is ways to desingularize it, for example, by putting a U1 into a non-abelian group and then ending up via Higgsing in this standard Polyakov monopole business. But in the pure U1 theory, this would be a singular configuration, but then allows this deformation of this magnetic flux through the sphere to nothing. Okay, so in our setup, there is an alternative way. So Miguel described it more like I'm gluing some topologically non-trivial object into my spacetime. You can also think about it in the sense that your compactification manifold of type 2b is this non-trivial Bordism class. And yet, then you want to be able to deform it away. So you really want to be able to define a boundary condition, which would sit here in this case. Okay, and because we want some sort of notion of space-time still left over, we are interested in situations where the dimension of this manifold M here is 9 or smaller, and for basically dimension equals to 1, it was discussed by Miguel. So the topic is, well, is the Bordism group of type 2b 0? And you already know the answer because Miguel showed you the slide. This is highly non-trivial, and most of them are non-zero. And if not, well, what are the defects that we need to include? So what are the analogs of the magnetic monopole that we need to include in order to break the global symmetries associated to the Bordism classes and then allow the deformation to not? Okay. And so it's an approximation in the sense that the only information that we're relying on in the structure that we implement is that of the space-time manifold plus the duality bundle. So for example, we have no control, or we don't implement something like Ramond-Ramond fields, or even more a better description involving, for example, the K-theory charges that will go beyond just the Ramond-Ramond fields described in differential cohomology, for example. Okay, so I don't tell you again what the structure of type 2b is. So I just flash this slide here, that these are the corresponding groups. So one is the spin MP2Z, that's the fermions. The other one is the spin GL plus, where you also have world sheet reflections, or -1 to the FL. Both are the same in this class. Okay, so in order to derive those classes, Miguel already told you that you need to take the path of the mathematician. In our case, that's Aaron de Bray, who has all the knowledge of these magical theorems that you need to use, and you can go through this derivation in the paper, which we really spend a lot of time on, to also give an introduction of the techniques, sometimes also a little bit of a physical intuition, even though we were not yet able to describe the atom spectral sequence really with all the physical intuition we would like to. Just maybe a bunch of keywords here. So you start with this big construct, right, of this omega spin MP2Z. And what you want to do is you really want to break it up into easier pieces. And for example, for MP2Z, it's easier to describe it in sort of a prime decomposition. And for that, it's useful that MP2Z is an amalgamated structure. So it's sort of, it splits up into easier parts. And those can then be tackled separately, and then in the end you combine everything into the full setup. And the atom spectral sequence plays a crucial role exactly for this prime 2 part of all those groups that appear. And when you have the Bordism groups, so I can flash the next slide here, which are highly non-trivial, your work unfortunately is not done yet, right? So this atom spectral sequence will tell you these numbers, or at least give you a good idea of what these numbers should be. But then you have to find manifolds which actually are generators of those summations. And again, there is no real constructive approach. So there is no rule book, and you start like this, and you will be guaranteed to find the correct generator. And actually, a lot of this is educated guesswork. And of course, it depends on how does it, whether it's more educated or more guess work in these cases. And actually, some of the generators here took us a lot of time to find. Okay, but in the end, we have a full list of the Bordism groups as well as a full list of representatives. And now we want to find string theory defects, or defects that we can interpret in type 2b string theory that kill these associated global symmetries. And that brings me to the first part, which is the rise of Metaplectia. So what is this spin MP2Z structure, or what is a spin MP2Z manifold? So nicely, there is a different interpretation. A spin MP2Z structure is actually a spin structure for a manifold which has on top of it a torus. So it's a torus fibered manifold with 2 more dimensions. And of course, if you hear that, all your alarm bells should go off. That's F theory, right? So there is no, in principle, there is no supersymmetry here yet, but at least you have this torus vibration structure, which should remind you a lot of F. And of course, it's related. This duality bundle will act on the complex structure of this F-theory fiber, which describes the axiodilaton, which is acted upon by this duality. So everything makes sense. And now the picture becomes a bit more refined. So we have our space-time manifold, which is this M that I showed before in this compactification space. We have some non-compact space-time piece here. And then on top of all of this, we have a torus fiber that sort of captures the information about the duality bundle. Okay? So you can go around 1 cycles and your torus will undergo monodromy transformation, for example. Okay, so just to repeat what Miguel did for spin MP2, but now really displaying the F-theory torus if you want. So the only manifold we have to consider is a one-dimensional closed oriented manifold. That's the circle. You go around it, you do a MP2Z monodromy transformation. So this means that your torus undergoes a monodromy. And now you want to find something that is for which this is a boundary. And that is the 7-brane picture, right? And now you see that as in the monopole, we now end up with some singular configuration because we know at the location of the PQ7 brane, so that would be at the tip of this disk if you want, the torus, the fiber torus pinches, and that tells you that this is sort of a singular fiber structure here. Once you include these 7 branes, the global symmetries associated to this large Cobordism group Z24 are all broken and so are absent in the quantum gravity theory. So by doing this, because Cobordism is a very coarse kind of classification of symmetries, you lose some information. So if you want, for example, to get something like non-abelian exchange statistics, you cannot really work with this Cobordism that is a abelian group. You have to put a bit more information in to also get more information out. For example, if you do some monodromies of branes around other branes, what happens? And for that, I want to highlight a work that I did with Jonathan in 2020. Okay. So now so this is what you knew before. Now let's go down in dimension. So this was the 7 brane. If you have now omega-3, also non-trivial, you will find the generating manifold to be of the type of a length space. So a length space, 3-dimensional length space, is just a free quotient of a 3-sphere by this Zn group. And this has a torsion 1 cycle. And this non-trivial duality bundle tells you that you go around this torsion 1 cycle and you do a monodromy transformation, right? So that is our geometry. Again, we want this to be the boundary of something. So how do we describe it? Well, let's first describe the 3-sphere as a Hopf vibration. So that's a circle fibered over a 2-sphere or P1, right? Then this Zn action takes a nice form by basically acting like rotations on this circle fiber, right? And for this, we have a nice interpretation of how to describe it as a boundary, because we can just take the circle of the fiber and make it into a disk, right? And then this full space will have precisely this length space as a boundary. And what this turns out to be, so this is the Hopf vibration of the S3, and of course, on top of which we have the torus vibration that takes into account the monodromies of the fiber, can be closed into something that is a complex line bundle, O minus n over P1. And again, on top of which is the T2. But if you know F theory, you know this space, because this is nothing but a resolution of the non-Higgsable clusters, right? So non-Higgsable cluster is sort of a collapsing minus n, self-intersection minus n curve, or in the singular limit, you can simply describe it as like this 2 torus times 2-dimensional complex space modded out by this Zn, right? So the defects that we need to include are non-Higgsable clusters. So these appear, we never put branes in the picture, we never put non-Higgsable clusters in the pictures, but they appear naturally as a candidate of defects killing the associated Bordism. Right? And of course, non-Higgsable clusters are very important because they were sort of the easiest first example of geometries that realize interacting superconformal field theories in 6 dimensions. Okay, so that's exciting. Let's continue going down in dimensions of the defect. Yeah.
So Miguel said that it take the 2 defects to 7 branes and generate everything from it. So can you generate any other non-Higgsable clusters out of these?
So here I think you don't need all of them. I think in principle you need the -4 and the -3 curve. They kill the 2 factors that I showed you, the Z2 and the Z3. You can combine them, then you get the Z6 guy in principle, but you don't need to go up to a -12. However, I mean, you already, since they only include 7 branes that you had already, in principle, they're already captured. So you don't need some fundamentally new object, but you just need to recycle the object in now a very funny way inside this geometry. And it also, so what is interesting is that, so it's non-trivial that the solution or the Bordism defect that you need to include allows for a Kreppin resolution. And the non-Higgsable clusters here are a special example where this is the case, and we'll come to examples now, for example, here in dimension 5, where this is not the case. So the setup is very similar. You have a singular configuration, right? That's the monopole kind of that kills the global symmetry that you can describe as T2 times 3-dimensional complex space modded by Zn. Again, there's a torsion 1 cycle that will have a monodromy. And however, this you can now not Kreppinly resolve. This is a terminal singularity. Again, we know what this background is because this is precisely what was described by Dierigl and Iñaki, which is this S-fold configuration, which describes exotic n=3 superconformal field theories in 4 dimensions. So again, the input is sort of minimal, but the output is very interesting because we get non-Higgsable clusters telling us about 60 SCFTs. We get S-folds telling us about n=3 SCFTs in 4 dimensions. Now you might ask, well, what happens if I go further down in dimensions? Well, actually, these configurations are very generic in spin MP2Z Bordism. Oh, sorry. Yes, one thing I should mention is that actually there is 2 different classes. So that's related to Craig's talk yesterday a little bit. So there is 2 types of S-folds. These generate the Z32 summand as well as the Z2 summand. And as geometric manifolds, without taking into account the spin structure, they're identical. However, they are different when you include this spin, or better, the spin Z8, so a twisted spin structure on it. One of them will lead to an n=3 S-fold, so that preserves n=3 supersymmetry. The other one will only preserve n=1 supersymmetry. Right? And these are actually F-theory lifts of certain M-theory configurations. In those M-theory configurations, you don't have to choose different spin Z8, but really different spin structures that were discussed by Boviv and Bomans 2 years roughly ago. And because those theories are still very, very much related, we have some hope of showing that they're also in this funny class of n=1 theories that somehow have that the 2 central charges A and C are equal to each other, even though they don't have to be in n=1, but they have to be in n=. Okay, but that is work in progress that hopefully will appear soon. Okay, so now let's go really down further in dimensions. And as I said, so these configurations of torus times complex space modded by some sort of rotational actions are very generic and also appear now in the Bordism of dimension 7 and 9. And these are sort of new generalized S-fold backgrounds that you can describe as S-strings or S-instantons, because those are string-like objects if it's the defect associated to Bordism in dimension 7, or it's really point-like object in space-time if it's associated to this Bordism in dimension 9. Okay. I should mention that if you just take the geometry that describe and look at how the supercharges behave, in the S string case, they pointed like a very exotic type of supersymmetry where it preserved 8,2 SUSY charges. So this is the 2D version. So these are real supercharges. However, there's a caveat because I told you we don't know about the Ramond fields. So in principle, it might be that these objects, if you really want to make sense of them in full string theory description, they actually have to have some D1 brane charge or some fundamental string charge. If that is the case, of course, you would break more of the supersymmetry. So this is sort of the upper bound of the supersymmetry. And if we want to really extract the full supersymmetry, we need more detailed information of this solution. Funnily, in dimension 7, there's another class that appears elsewhere. Namely, it's something that we find in dimension 5, which is this lens space, Ln5, which is, however, now fibered over another space, P1. Okay, so now you have a fibration of some defect that you already found before over some compact manifold. But if you know how to close the fiber, as we do, because there was the S-fold we discussed before, we basically know how to close this whole thing here, because we just now wrap the S-fold on our base in the fibration. And because there is this non-trivial fibration structure that tells you that this is a topologically twisted theories, that appears naturally again from this Cobordism discussion. And the topological twist is precisely in such a way that you still preserve some of the supersymmetries. Okay, so you might ask, well, you told us a lot about odd dimensional Cobordism classes. What about the even dimensional one? Well, actually, for them, we don't have a good answer for the defect. So those are very, very much related to the spin Cobordism generators that were already discussed in Kumrun's and Jake's paper. So for example, for spin MP2Z in dimension 8, they're exactly the same. They're the bot manifold. So this is this spin 7 manifold, will appear later, and a two-dimensional hyperbolic projective space. However, sometimes they lead to some sort of refinement. So for example, in spin Cobordism in dimension 4, Miguel told you that the generator is K3. Turns out that in spin MP2Z generator in dimension 4 is half a K3, namely a Enriquez surface. And this half a K3 is also associated with some sort of duality bundle, which is described by this Enriquez Calabiao that appeared already in. Sorry, so I should the quotient of K3, the Z2 quotient of K3. Sorry, this is the correct. This is what I mean here. Okay. So let me summarize the spin MP2Z part. So funnily, because they all have a nice interpretation in F theory, all of those defects turn out to preserve a part of the supersymmetry. Okay. And they're very interesting because they give rise to interesting backgrounds that we know of, non-Higgsable clusters, S-folds, but also generalizations thereof, namely S-strings, S-instantons, and these intricate topological twists that, of course, were known before. So now let's go back and also include the pin structure, right? So let's again allow for reflections, not only this MP2Z transformation. So again, in principle, you can do that either including the world sheet orientation reversal or this -1 to the FL. They lead to related defects. Okay. Now, what you'll find is a sort of orientifold background. So for example, I give you one precise generator, namely S3 mod Z2. That's just a three-dimensional real projective space. Again, this has a torsion 1 cycle. You go around it and you encounter one of the reflections, for example, the world sheet orientation reversal omega. But this is precisely the action of a O5 plane. Okay, again, caveat, O5 plane has D5 charge. We don't know about that here. Okay, but at least this action is precisely what you would expect. Of course, again, you could describe it instead of omega with -1 to the FL, so a left-handed fermion number, and it would be something like a S-dual version of the orientifold. But it's not conceptually, it's not different. It will not kill a different Cobordism class. However, there's another generator, which again has the same underlying manifold, three-dimensional real projective space, but now needs a combination of MP2Z as well as a worldsheet reflection. Okay? And this probably breaks supersymmetry. Okay? Why? Because you can think about this as a combination of a R7 and some combination of PQ7 branes that wrap a -2 curve that you then collapse to 0 volume. Okay. Again, the question, what about even K? Well, again, many generators are inherited from either spin or spin MP2Z Bordisms, for example, the Enriquez surface. But again, there might be more refinement. So now, before I had the bot manifold, this spin 7 manifold, where the Dirac index is equal to 1. And if you go to spin GL plus, you'll find that actually you find half a bot manifold. So it's an 8-dimensional manifold where the Dirac index is equal to 1/2, which is not spin. So other classes that appear in the spin GL plus business are higher dimensional generalizations of real projective spaces, again with combinations of MP2Z as well as reflection monodromies, non-trivial fibrations, like a new class of real projective space fibered over other real projective spaces, some new type of topological twists that now includes reflections, and so on and so forth. Interestingly, all at least odd dimensional generators can be bound by something that contains only the R7 brane as a new ingredient. So you don't have to include more and more and more non-supersymmetric stuff, but this one brane is enough to account for everything. But of course, it has to be topologically twisted or compactified in interesting ways. So this is the story of the Cobordism conjecture in this regards. But if you ever done a Bordism calculation, then you know that actually the difficulty becomes more and more as further you go down or up in dimension or down in this list here. So there better be a good reason why we went up to 11. And the reason for that is because anomalies, at least the global part of anomalies or potential anomalies, are characterized by Bordism groups in dimension d+1 of the theory. So in our case, where we want type to be with a duality structure, we have to calculate the 11th dimensional Bordism group here. Again, this is highly non-trivial, has a lot of different summons, and all of them pose potential anomalies in the theory, right? This is not all that has to be done. Instead, you have to really set up the anomaly theory and then evaluate it again for each of the generator of those classes in order to check whether really these anomalies are realized in the theory. We did that, and it turns out, indeed, there is an anomaly for type 2B duality. Okay? And of course, this is terrible, but it turns out it also can be canceled. And there is, Miguel mentioned it, it can actually be canceled in different ways. So there is the possibility of just including new topological sectors, and that's related to the question whether there can be more topological theta angles or non-invertible faces on top of that. So this would be a realization of this first cancellation mechanism, right? The version of topological Green-Schwarz that Iñaki and Yuji and collaborators discussed a couple of years ago. But it's sort of, this is ungeneric because there's a lot of different ways in order to cancel the anomaly. That's why we actually prefer the second one, which is like a discrete Green-Schwarz term involving the self-dual four-form field. And if you realize this, you'll find that you can cancel all the anomalies, at least the one that we could calculate. This is all but two different ones. There are Z2 classes, can all be canceled by including a single new term, which is very topological, could never be detected by local dynamics of type 2B because all of them are torsion classes, but a single new term in the type 2B action, which is of the form F5 wedge. Well, has to be more refined than wedge, but of this type in the wedging some characteristic classes that depends on the duality bundle as well as some tangential structure. Okay. But of course, if there are more possibilities, there's a question. Are all of these possibilities allowed? If yes, then in principle, there's a discrete landscape, even in 60, because I could consider UV completing, preserving my duality symmetry by either switching on this topological green Schwarz or a different topological green Schwarz, or maybe some of them are not allowed. And of course, these discrete theta angle that Miguel discussed are in the same category of things. So this would also contribute either to a discrete landscape or like a topological swampland. And while we find, of course, one of the mechanisms, because it's sort of uniquely defined to be more beautiful, that doesn't mean that it's the right one. And it would be interesting to see whether the other ones are ruled out. And with that, let me come to my conclusions. So I hope I showed and continue to show that the investigation of Cobordism groups is very general and very surprising, because the input information is sort of rather minimal, while the output is pretty astonishing. At least we were surprised of what we could extract from all those Cobordism calculations. Find very interesting backgrounds, either known or generalized, non-known situations, which of course shows that the Cobordism conjecture offers a lot of interesting tests as well as predictions in this setup of type 2B. Now, for future directions, I think this is only the start. We already heard great ideas of, doing it for U-duality groups or other duality groups that fly around, tracking what happens with these objects under duality, to other string theories like type 2A, M theory, or even heterotic. Right? Maybe we can use this R7 brains, or maybe configurations where these reflections arise, in order to build new kind of theories that are similar to F theory, but now allow for reflections. So maybe one could call it like, maybe one can call it like this. So Fe, or we don't know how to pronounce it yet. And yeah, of course, this, what? Yeah, and that's it. Thank you very much for your attention.
Thank you. So I had a question about your Metaplectia story. So there, we have your first report to produce Omega 1, and that really goes off by putting key seven areas. And that was sort of the story I learned since you started. And I'm curious how much of the other versions you think would go away if you include because your report is so about singular fibers. So if you just include key seven areas, how much data, how much goes away? How comfortable is this since you?
So I think at least the Cobordism groups for spin C should be known to the appropriate dimension, and then you can just compare and then try to match those things under this matching. So what is useful here is that sort of what we find is in between spin and spin C, because what we actually, so this prime decomposition, if you do it, then it will show you that it's something like omega k spin with BZ3. That's one of the prime factors. So then you find basically the spin generators and something that is related to this discrete Z3 gauge theory, right? But the other part at prime 2 is a spin Z8 structure, right? And this is exactly in between sort of spin and spin C structure, in the sense that if you would have a spin Z2K structure, you can send K to infinity and sort of recover something like spin C. Yeah. So this is what I can say. I don't know exactly how the map goes.
Because the structure you want something like math, so you go from the map to the packed by the moduli standard with the curves or something. And that's not the same thing as you figure out.
Is there a need for our reason why the objects that you need to add to the triviality factors in the Metaplectia are going to reproduce in the geometries that we did.
So this is a very good question, and the answer is yes and no. So so as I already mentioned at some point, so it's sometimes, so it's a very tricky business of course, every spin MP2Z manifold is also a spin GL plus manifold, right? So in principle, all of them are valid candidates for generators. But spin GL plus manifolds also allow for more deformations, so they might be trivial. And actually the way whether they are trivial or not follows some rules, and sometimes the obstructions can be phrased in cohomology classes of the duality bundle. And basically the transformation properties of this cohomology class under these reflections will tell you whether the generator survives or not. So if you go back to the list of Bordisms, you see, for example, that here you will find more, then you find less, then you find more, and then you find less. And this is precisely the periodicity in terms of what type of cohomology class is odd or even on the reflections that will be met between those guys.